Hey everybody, welcome to the Azure Cosmos DB Global User Group for September 2024. Jay Gordon, I'm a Senior Program Manager here at Microsoft, and I'm your host for today's session. I love doing these. We meet every second Tuesday of the month, or at least we try to do every second Tuesday. And what we do is we bring together members of the Azure Cosmos DB community, and we try sharing what we're working on and connecting with fellow developers. And this show is driven by you, the viewer, our community members. So we encourage you to take part in this by asking questions or even volunteering to present at a future session. I'll be sharing with you intake forms so that you can share with us your idea and come on the show just like my guest. So you'll see it in the comments, and also you'll find it in the YouTube description. So today I've got a really great guest, and I'll talk a little bit more about him and what we're going to be talking about in a few minutes. But first, I have my partner in crime, Askia. How you doing?
Good, Jay. How are you?
I'm good. I'm glad that we are back doing this week.
Yes.
These are so much fun, and you and the rest of the Reactor squad, you helped me out get these done. I really appreciate it. And I know you're going to be telling us a little bit more about Reactor. But first, I know you've got a little bit of housekeeping you need to do for us.
Yes, absolutely. Thank you for that. And yes, so as Jay mentioned, my name is Askia. I am the one of the event planners at the Redmond Reactor Space, and we've got a few things we'd like to go over. So if you could take a moment to read our code of conduct, basically what it says is that we seek to provide a respectful environment for all of our audience and presenters. We definitely encourage engagement in the chat, but we ask you to be respectful, mindful of your commentary, and if possible, please remain on topic. We're going to share useful links throughout the chat, so keep an eye out for that. And please keep in mind that these sessions are going to be recorded. They will be available on demand on the Microsoft Reactor YouTube channel, and that's typically within about 24 to 48 hours after this session ends. We are scheduled to go for approximately about 1 hour, and there'll definitely be time for questions throughout. So with that said, I will turn it back to Jay and see what's next.
So Reactor does so many great things, and I really appreciate it. If you don't know what the Reactor is, they are the people that bring sessions like this to you via either in-person events or here in the virtual like we are today. I know we'll be speaking again at the end of the show, so thanks a lot, and I'll see you later.
All right.
Cool. So as always, we try to come here and bring you a relevant subject to you, the developer, the user of Azure Cosmos DB, or someone that may be curious about how to get started. We try to have interesting topics to bring to you, and I've got a really great guest today. So today I am excited to welcome Shahab Kanji, who will be showing us how to build event-driven systems at scale using Azure Cosmos DB. So we'll explore how Azure Cosmos DB serves as a solid backbone for message-driven systems, whether it's transactional, outbox, or a full event store. He's going to share some best practices about data modeling, scalability, and how these all these different principles can help you build a resilient and scalable system to handle some real-world challenges. So just to kind of set some context, what is event-driven architecture? Well, it's a design pattern where events trigger actions in a system. It enables real-time responsiveness, scalability, and flexibility by allowing loosely coupled components to react to events independently. So like an example of this in the real world, which say be like a ride-sharing application. So when a user requests a ride, an event is triggered, and that updates the driver saying, hey, here's a new fare for you. It sends notifications out to the user, to the driver, and then it actually calculates how much the fare is going to be in real time. So all these things happen independently, and it enables the scale of the system as there are more drivers and more users that are interacting with those drivers. So that's my really cheap description. It only costs you a few seconds of your time. But I have someone that's my guest today who's going to be giving us so much more than my $5 introduction. And that would be yourself. Shahab, how are you today?
I'm doing good, thanks. How are you?
I'm doing well. I'm so glad to have you join me today. You kind of did this the way I say to everyone else. Like, if you have something interesting, send it to me, and that's what you did. So before we kind of get into your technical presentation today, I'd like to learn a little bit more about you. I think it's important to just set some context. Why don't you tell us a little bit about who you are and how you came to being with us today?
Yeah, thanks. Thanks for having me. First of all, I'm Shahab. I'm working currently as a coding architect at a company named Square, which is based in Vienna. And I've been in the industry for, I don't know, for more than 20 years, like from 2003, 2004. And I kind of grew up with .NET. My first applications was .NET Framework 1.1. And I started from there and touched upon different corners of software development. And now I'm focusing on software architecture and software transformations. And I need to deal with some systems to be scalable and like loosely coupled components, software components to be designed. So they need to talk to each other in a way that all of them could be scaling out. And scaling is like a factor in the systems that we are working currently. And we used Azure Cosmos DB for some of our designs, like in 2 years ago, from 2 years ago, 3 years ago, we were heavily working with this product from Microsoft. And then I thought this is a great community to share what we used for.
I think it's a great community too. So thank you for being part of it. So I think I've kind of given everybody a little context on what we were going to be talking about. And that means that it's time for you to actually dive in. So I'm going to be bringing up your presentation. Everybody, if you have questions, I'd love you to leave them in the chat and we'll address them as soon as we can. But until that, I'm going to hand over the floor. So take it away.
Thank you so much. Yes, thanks everyone for participating. Today we are going to talk about building event-driven systems using Azure Cosmos DB as part of one of the components in our system. And what I usually like to do is always like taking a look into the basics and trying like to connect the dots from different perspectives and bringing it into a complete picture. I already introduced myself. You could also follow me on social networks with @Genji. And let's dive into the problem and the stuff that we had. We were all good since we always had this all valid architecture diagram that we had a client sending a request to a server, and then the server serves the request by communicating to a database and storing some data there, fetching data, and bringing the data back to the client, right? Everything was all good until our companies are growing up and more requests are coming, more clients are there. And then we have a problem that our server might become the bottleneck, not being able to handle all of these requests that are coming to the server, to the software we are providing. So we all kind of know the solution, right? We are adding more servers, we are scaling out our service, and then the load of these requests could be balanced between these servers that we have, and then they are talking individually to the database, serving the requests. Still everything good until the load is again too high and the database would be under pressure. So me and my colleagues in our company sit together and decided like how we could leverage the load and reduce the load over our databases. And then we decided to go to kind of an asynchronous mechanism. So we have an application that could, on its own pace, pick up these requests and process them, and if necessary, save the data that is required in a database. So we kind of use the web queue worker pattern. The client sends a request to the server puts a message in a queue, and then some other component in our software system would pick up the messages and then process those messages, and if necessary, stores data on the database. And again, everything is good. If we have more clients, we could just scale out. We have asynchronous communication, putting everything in the message. The only problem is that the messages could get a lot of messages could be in the queue, and the worker cannot process all of them all together. And then we have a solution for that, right? We scale out the workers, then we could process the messages in the queue faster and faster and communicate to the database again. Again, the database will go under load and would become the bottleneck. So we thought it seems that we are just moving the bottleneck from one place to another place, and we are not really managing the issues for scalability. And so we thought that this kind of asynchronous communication sounds great. All of my services and the workers and everything is kind of decoupled from each other. I could scale out them based on whatever suits the requirements of that specific server. But we always have this database under pressure. So we decided to go with event-driven architecture. With the event-driven architecture, we could design our system and components to respond to events and to things that are happening in the system. It has three main components: producer, event broker, and a consumer, which the name suggests. The producer publishes events and commands to the system, and the event broker routes those commands and events to whoever is interested in these things. And as the name suggests, also the components of your software communicate over events with each other. And it is important to use this when scalability is an issue and is a main concern, and you want to promote loose coupling between your systems. There are two parties that are playing a role in event-driven architecture. One are events, and the other is commands. So they're a little bit different from each other, and it makes sense like to get to know what's the difference between them. So events are things that already happened in the system. They are facts in our system, and they are immutable. We cannot change them. They are here. One example is that when you transfer money to another bank account, if you want the money back, or if the money was you put an order and now you want to return your order, then you need to get a refund. So these are facts that are happening in your system. While commands are invoking behavior, they are asking something from a specific component in your system to do something, to save something, to fetch something from the database and return the result, right? The other difference between them is that commands are usually point-to-point. The sender of the command knows about the receiver and knows what they want from it, and they expect something from the receiver to do. While in the events, it's more like a publish and subscribe. So something just has happened in your system, and you want to notify everyone else, right? And if those other software components are interested in doing something, or then they could subscribe to this event and they could get notified. Another thing that is very important is who owns the contract when we are designing our systems for the event-driven architecture. Because it is not that we are totally decoupling everything from each other. We are just moving the coupling to somewhere else, and we want to have a managed coupling. So it is always like this, that we are not removing the coupling altogether, but we are managing the coupling better if the system could grow, right? So we need to know that who owns the contract because of all the things that are regarding the versioning of the system, being backward compatible or forward compatible. We need to know that. With the events, the sender owns the contract and should maintain the contract. While with the commands, it's the receiver. Like the sender doesn't have anything to do with the contract. It just knows that the contract exists and could send it, right? It's the receiver that needs to manage it. Number of consumers, number of senders are different. And obviously how we describe that in our code and in our system and is for events based on past tense, because they have already happened. And for commands, it is an imperative verb because we are asking for something. Speaking of events, there are three types of events that we should know. One is the unkeyed events. These are events that are describing a singular fact and statement. They are not necessarily, we don't necessarily need to group them with other, with other events together. These are the unkeyed events. We also have entity events. Entity events are describing the state of the event at any given point in time, and they are having the values for all properties that this entity contains. An entity is a unique thing with a unique identifier that distinguishes it from the other entities in our system. The keyed event, which we will need it like later on when we are designing our system, it has a key, as the name suggests, right? And this key does not necessarily represent an entity. It is used for partitioning the stream of events that are kind of logically belong to each other, for guaranteeing the data locality within a single partition of those event streams. So it needs to guarantee that all of these events that share the same key or having the same key will be located somewhere close to each other. So later on, if we want to process them, we could access them faster and cheaper. For event-driven architecture, there are related patterns that emerge. Even though these patterns like CQRS and event sourcing, they are not necessarily used together, and you do not have to necessarily use them together, but they are kind of a fit with each other, right? And so CQRS enables us with having separate read and write models, and it enables us for optimizing performance and scalability. This stands for command query responsibility segregation. So we are separating the command part of the application from the read part of the application, so we could scale them based on the requirement of each of them. Event sourcing, on the other hand, event sourcing captures every changes that we have in the state of the entity. Instead of storing the entity itself, we are storing the changes that are happening. So we will automatically get an audit trail in our system, and we could easier handle the transactions, complex transactions, and we could also replay what has happened in our system. If we have a new algorithm, for example, to have fraud detection, and we want to test this new way of fraud detection compared to our older version of that, we could replay the new one over events that are already in our system and compare the results and see which one is better. And as said, you don't necessarily need to do these things with each other. And Jimmy Bugard has a very good article about these things. So the link is here. You could later on read the article. We ended up with this architecture. So we wanted to use, we have our client with that sends requests to our web API that was hosted in Azure App Service, so we could scale out that independently. And this database is now, this API talks to our Azure Cosmos DB. We will see in momentarily that why Cosmos DB could help us to scale out our database and not becoming a bottleneck anymore. And it also enables us with a stream of changes that we could listen to and publish our messages to something like Azure Event Hub or Azure Service Bus or any other kind of message broker or event broker. And other services like inventory service, email service could register to those events, do whatever is necessary in that business scope to be done. We have a specific Azure function here. We will see that later on as a code example. I just named it a snapshot. It also listens to the stream of changes that are coming from the Azure Cosmos DB, and it generates the latest states or generates the read models that we need for our API to be able to fulfill the requests that are coming from the client. So that's why it's also writing back to the Cosmos DB. So now that we know a little bit about events and we know a little bit about like why do we need a scalability in our system, let's take a look into Azure Cosmos DB. It's a globally distributed database, which we could have an instance of this database with just one click in the portal, and then we will have like another instance over the globe, right? And it scales horizontally. We will see how scaling works for Azure Cosmos DB and how it could give us a provisioned throughput. It's also a multi-model database covering from graph databases, from key value databases, from document databases. When it comes to scalability, we always have three dimensions of scaling based on the Art of Scalability book. One is a database per application. So we have our inventory system, we have an order system, they could have separate databases. Even one application, since I'm living in Austria at the moment, so we could have my company.at and its own database, and they are for customers that are in Austria, and we have mycompany.com and with its own separate database. Even though both applications and databases are looking the same, they are just serving different kind of customers and functionalities, so they have like separate databases. The other aspect is scaling by cloning or horizontal decomposition. It's replication. So you have one instance that is for your writes. You could replicate the data as it comes into your database to other read databases, and then you could load balance the read request to other things, so you could scale your read model. The other way is sharding. Sharding or data partitioning is splitting similar things. That means if I have a web shop, for example, and I'm getting orders, I could split my orders into smaller chunks and put them in different places. So I need to deal with smaller amount of data instead of a very big data. We will take a look into sharding, which is how we could scale Cosmos DB in kind of infinitely. So with sharding, we always have a single logical database, even though there are like a cluster of databases behind the scenes for it. But the thing is that the nodes have different data. They are similar. They are the same type of data, like orders, like customers' data, like IoT data, right? But they are not the same thing. They are different values. Like order 1 and order 2 are two different things from each other. How it works behind the thing is that I have a logical database with some data stored in here. And as the load is increasing on my database, I could spin up as much as physical instances as I want and spread the data there. These are our events that we could store on different physical instances. And how our application communicate with that is that when a read or write request for an event comes in to the logical database, it knows where those events are stored based on the partition key, which we saw earlier about the keyed events. So that key that we are defining is kind of the key for the logical database to route these requests that are coming there. So if another request for the green events come in, it will route it to the physical instance that actually holds those data, and that will be processing it. So this way we are loading the data between the physical instances. And it is important that this partition key or this key that we are choosing for our events has a fair distribution mechanism between the physical instances. We will see why that is important. So with this way, the advantages are that each server deals with a subset of data, right? Instead of dealing with terabytes of data or petabytes of data, they could deal with gigabytes of data, which also improves transaction scalability. Previously in relational databases, we had this situation that if you lock a table, like all the other requests needs to wait in the queue. So for the lock to be processed, and then we go that. Here it's less. We have fault isolation. If one physical instance goes down, not the whole system is down. Cache utilization and reducing in memory and I/O usage. But also there are disadvantages. We have complexity in our application. We need to deal with all of those things. How do we design a partition scheme? Because this is important. If we design a wrong partition scheme, we might need to do a repartitioning. What if the key that we already chosen for our system is not properly distribute the data, right? And we might also have improper traffic distribution. Considering like that I have a show and Taylor Swift have a show, right? And our data are stored in different kind of physical instances. Obviously, the server that has my data stored in it would not get enough traffic for that server, right? And so we have improper traffic distribution. Another problem that is coming with the designing of a partition scheme is performance issues with queries. So we are storing all the orders, everything like order accepted, order requested, order delivered, all of them based on, let's say, order ID in one partition, like in locality of each other. What if our request is how many orders are accepted, how many orders are delivered? Now we need to go to every physical instance, ask them to check every document of order, and then responding back to us, right? This is similar like to table scans in relational databases. It's a very huge and expensive query. So we need to deal with these things as well. To get there, how these disadvantages, how could we tackle those things? We need to know some concepts behind this, behind Azure Cosmos DB, how things are designed. So every document could be 2 megabytes. These numbers are your friends. You need to remember them. And every logical partition is 20 gigabyte of data. Logical partition is a group of related documents that are sharing the same partition scheme with each other, the same partition key. So they will be grouped logically together. And it is guaranteed that every document that has the same the same partition key will be stored on the same physical partition as well. And the physical partitions are 50 gigabyte, could store up to 50 gigabyte of data and serve 10,000 request units per second. The request units are measured for how much your Azure Cosmos DB would cost, depending on the storage, memory usage, CPU usage, and all of those factors. And considering that you have a document which is 1 kilobyte in size, and you know its partition ID and its ID within that partition, so Azure Cosmos DB could directly go there and pick up your document and return it to you, it will cost you 1 RU. About the transaction, we mentioned earlier that transaction management is better. So in Azure Cosmos DB, the transaction scope is the logical partition. So if I put 2 documents into a transaction batch and send it to the database and everything goes well, they will be stored. But if something goes wrong, then that document will not be stored. So it gives you ACID features within a logical partition. And how you are designing this partition key, we could give you a very good separation of concerns between things that could not have conflicts with each other. For example, orders of customer A never have conflicts with orders of customer B, right? So maybe customer ID in this scenario is a good partition key to manage, to give better transaction separation between different kind of requests that are coming to our system. Let's see some code here about transactional outbox. Let me see. So where this transaction management could help us is that previously we had this situation. This is an API application we provided. It has an API that if I just run the API, for example, it has a Swagger endpoint. It just accepts an order. We have a create order. We have a create order command coming to our system. We are creating an order. And within this order, we also want to raise domain events to inform others that an order is placed or an order is created or accepted. And then we are storing the order and we are emitting even the events of this order for other systems to be notified. After a couple of days, we observed that we have orders in our system that never got delivered, never got updated, and the inventory system never find out about those orders. And after debugging, we find out that at this line 22, sometimes the application crashes. So we are storing the order, but we are not able to notify others about what has happened in our system. Also, moving these 2 lines, like first informing others and then storing the order in our system, does not also solve the problem, because we could inform others. Now the inventory would reduce something, and we are not storing the order itself. So here there is a pattern called transactional outbox pattern. every database that supports you with transactions and it gives you the ACID properties, we could implement this feature. So in our implementation, we introduced a unit of work in our system. And instead of directly writing at line 21 to Cosmos DB and also at line 23 publishing to Azure Service Bus, we just wrote all of those things into an in-memory database. So we created an class order container context as our unit of work, and it has an add order and add events. And both of them are adding into a list or whatever collection you want to use. Here, it's just about concepts, right? So we have here in-memory things, and then we are creating a transactional batch. Let me reduce this. So we are creating a transaction here with Cosmos DB over a partition key. So we decided that the order ID for the events that are happening over our order entity, like order created, order canceled, order accepted, they could share the same order ID with the order itself, and we could store all of them inside the same logical partition, so they will share the same partition key. And so we are adding the order itself to our transaction, and we are adding any event that it has raised or exposed to our transaction. And then we are committing all of them together, right? Let's see that in action. So I ran the API. Let's run my fancy consumer, and let's run the message relay. When you want to deal with transactional outbox, there is another component. It's called message relay. It picks up the events that you're supposed to publish to the broker, but instead you save to your database from that document, from that container, or from a table, and then it publishes that to actual broker. So if I have now the run, I think here, or is it this one? So let's have our fancy consumer. It listens to an Azure Service Bus and publishes the messages there. So I have this CDB global user group database. And if we go to Data Explorer, I have created this web shop, which has the orders collection here. Currently, it is empty. If we go to our Swagger endpoint, we could just try posting some data, let's say 1,000 of this product, and execute. We got this order ID back. And if we go to our application, hopefully everything is running, and hopefully this fancy consumer would get the data. Okay, let's get here. Let's refresh whether I see. Okay, something went wrong, obviously, on my side. I don't have the orders.
Well, while you're thinking about that, we do have a couple questions if you'd like to answer
Yes.
those. Great. So we've got two from Thomas. And so the first question is, what is the typical response time for requests to the database that uses sharding? And what is the most efficient cluster structure for data repositories?
Sorry, what was the second part of the question?
What is the most efficient cluster structure for the data repositories?
Okay. The first part is usually the response time is, I think, 1-digit milliseconds with Azure Cosmos DB. And the things for cost, like the storage cost is, for example, indexing. It also costs you a lot. And what we did with one of our systems that we implemented the event store, since for the main things we always need to do, we could always do a point read to our database. So we kind of disabled all indexing over every property, and it like reduced some of the costs for us regarding the storage.
Great. Okay, and we have one more question. Same person, Thomas, wants to know, can there be supervisory rights with respect to transactions that avoid the batch process?
I didn't follow the question. Sorry.
Yeah, I'm not too really sure. Thomas, if you want to kind of expand on what you're asking, can there be supervisory rights with respect to transactions that avoids the batch process? If you don't mind diving in a little deeper, we could definitely use your help. So that being said, why don't we let you continue with your presentation? We've got about 25 minutes to go.
Okay, great. Then let's continue with the presentation. So we kind of use this transactional outbox, and we had our entity and its related events next to each other, and we thought it looks familiar to event sourcing. So why don't we use event sourcing? And at the same time, we had this requirement that we got customers in North America, and we had to also deploy another instance of Azure Cosmos DB. So we thought for dealing with this kind of different, like globally distribution, multi-regions, we need to know a little bit more about what's going on inside the behind the scenes for our instances. So if you usually have one region, so considering West Europe, you will have a leader and 3 followers, and they will replicate any rights that are coming to your leader. It will be replicated to the followers. And here we always have a network in place, and this network is always something that we learned when we design a distributed system. We need to make sure we are not following the pitfalls. The pitfalls are that if you consider the network delay is 0, or you consider that you have unlimited bandwidth in your network, you might design an application that does not really perform well. So here we also, even though they are in the same region and the connection between them is super fast, but still there's a network. And we always need to decide between different things when it comes to distributed systems. So there's a CAP theorem, and it has 3 concepts in place. Consistency means that if I write something, can I read my writes like my latest write? When can I read my latest write? And there is also availability, like the system is always available. So every request coming to the server will get a response back. So no errors, something like that. And then we have partition tolerance. That means that if something in a network distributed system, if part of the system is not connected and not reachable, how tolerable my system is and how it could respond still to the requests that are coming to the system. And because of the fallacies of distributed systems, and that we know that the network is kind of inevitable, is part of our system, so partition tolerance is always there. And we kind of need to choose either partition tolerance and consistency. So always the reads follow the latest write, something like the relational databases that we had before. Or we switch to, this is the wrong one, sorry, switch to availability and partition tolerance, like this red part, because this is unavoidable and we need like availability. So something like in the cloud, we have multiple instances going on, but we might have some delay to deliver the data that we already write. And with Azure Cosmos DB, we deployed 2 instances, one in West Europe and the other one in the South Central US. And then the architecture changes a little bit. So when you have global distribution, one of the followers will change to a forwarder and sends the data over the network to other regions to sync the data. So even the delays might be a little bit more. If I'll go to portal, you could see how they are. If you have your instance and you go to default consistency, why something is wrong now? Let me refresh the browser. It seems like a rule that presentation breaks everything. So
that's the way it works. The presentation guides, they're cruel at times, but
yeah,
we're with you. We got you, and we've got about 20 minutes, so go for it.
Good. I think we should be fine. So here, for example, you see it takes like 255 milliseconds to replicate the data from West Europe to Australia Central. And as you see here, I'm also liking the consistency page of the Azure Cosmos DB, which is important to know because when you have global distribution, you also need to design your system and also change the processes within your business to reflect what is best for you for the consistency. Let's take a look into how they differ from each other. So the first thing that we have is the strong consistency. As the name implies, every read will follow the last write. So here the notes are kind of separate documents or different versions of the same document. It doesn't really matter. I'm writing in West US 2, and then if I read from West US 2, the same region, or East US 2 or Australia East, different regions, I will still have the latest write. Of course, I have consistency, but that means that I'm losing in some performance, right? Because if I'm writing to SUS2, I need the Azure Cosmos DB needs to make sure that this write is replicated on every instance. So if I read it again, I will get the latest one. A less strong one is bounded staleness, which means we have a maximum delay of 100 versions of a record or 5 seconds. And that means if I write to one region, I will still have my read will still get the latest write. But if I want to read from different regions, it might take some time for the data to get replicated there. And this amount of data is like 100 versions or K of a document or a record or 5 seconds. The default consistency level is session. Here, if I write in West US 2, still, if I read from West US 2, I will get my latest write. For East US 2, it has one thing in here called in session A, which is the same as in session A in the other ones. And that is like a token that Cosmos DB provides us. So on the next reads, if we provide that token, it means that we know which session we are. So it could detect where we were, and it could give us the latest write. If we lose that, then we are in a different session. So we need to wait until the data is replicated. We have consistent prefix. The consistent prefix is more about transactions. So if I have document A and document B, and in transaction 1, I change those documents to version 1, and in transaction 2, I change document A and document B to version 2, I will read them in the different session, in a different session. Either I'm getting both version 1s of document A and document B because it was in one transaction, or version 2 of those documents. But I'm not seeing document A version 1 and document B version 2. This could not happen. And the least consistency level is eventual. And it means that at some point, if you don't have any more writes, you will get all the latest write of that document on every region that you have. Otherwise, you need to wait some times, and the times might differ based on the latency between the networks and things. Why this is important? Because it's not just a technical thing. It also implies that you need to change your business process, and maybe your end users also need to have a change of behavior in how they are using your application. So this is something you should always consider in your design, and talk about it with your product owners, project managers, and those people. All of these things are good. So I could write stuff, events. I could write my events to my database, and they will be propagated to different regions. But this is just my events. How could I create things that fulfill the read part or the query part of my application? And that's where the change feed from Azure Cosmos DB shines. So Azure Cosmos DB provides us with a change feed. That means that every update, every insert, every delete that happens in a container of Azure Cosmos DB for any document, we could consume those things in order. And consuming events in order is one part of important part of event sourcing and event-driven architecture, because the order that these events have happened are important. We could use the change feed to trigger some actions on other systems, send notifications to the users. We could have real-time data processing, and we might want to migrate the data to some storage for, I don't know, for analytics and this kind of stuff. So you could use the change feed to leverage that. So as we talked earlier, we have a logical database. A change is coming that will be saved on one physical partition, and the changes as they are coming, they will be stored, and we could consume them in order. Why I'm showing the separate physical partitions here is because you could you could parallelize the consumption of the events for each physical partition. So you could gain scalability again for when you are consuming these events in your system. And since the events are grouped into logical things, so the red events and the yellow events are separate things. So it is important. It doesn't matter if I consume one from the yellow before or after one from red, because they are logically separate from each other. But it is important that I consume those things in order within their kind of group. And this is also another example of how we could use Azure change feed to communicate between different services. They could have our order event store, and we will see how we implemented event store. And then with the change feed, we could have different functions and different things consuming those events and doing their processes. One important thing, which I kind of learned it the hard way, is that you could, even with the change feed, request for a specific partition key and just get the changes for that partition key, and not caring about other partitions and in your system, which is a great feature, but it was somehow hidden, and I find it like very hard. Okay, let's see some code. Hopefully this presentation works better. Okay, then let's switch to another one. So we decided to design an event store using Azure Cosmos DB. And with event store, we have one method, which is the append. And append is just, we are appending events as they are coming to the end of the logical partition that we have. And we are using the ID for those things. So I have this event, and this event has a stream ID, which is the keyed event, the key for our keyed events. And then we have a date time that's happening. We have an ID within every partition. You need to have an ID. So that's how we decided the ID to be this created at time that we have in our system. So if I have a customer, I'm creating, I'm attaching the event to this transaction batch that I have. I will describe why I have a transactional batch in here as well. But just for now, we are just appending the event, and then we are saving those things into our database, right? When you are using event store, there are two ways to create a projection or a snapshot of the current status of the entity. One is synchronous. That means that within the same transaction that is happening, I could apply the event over the entity that I have and get the latest status of this entity and store that within this transaction. This is called synchronous projection, and this is totally valid. So this is also one of the misconceptions about, for example, CQRS, that you need an eventual consistency system to use that. No, you could synchronously create your state. And this is one part. This is the part that is publishing the events and storing them in the Azure Cosmos DB. The other one is the Azure function that we have here to read those events and apply them and generates a snapshot of the system for us. So with Azure Cosmos, with Cosmos DB trigger function, we have an Azure function. Cosmos DB trigger. You provide the database name and container, and we need a list container. The list container is for keeping track of how far this Azure function has consumed the change feed for this container that we mentioned above. And yeah, here we are getting a list of those events. We are looping over them, trying to fetch the latest customer instance that we have, if there is any or not. If there isn't any, So we try here to read them by a point read. And if there's any, we are returning that resource. If not, we are newing a customer and we are applying the event, and then we are saving that into our database. And let me run this Azure function.
And just to give you an update on time, we got about, let's say about 7 minutes or so before we need to wrap up.
I think after this demo, I think we should be fine. So in here I have a Cosmos DB runner. It's just an application. I'm creating like a new customer created event. Then I'm creating an email updated event, and then I'm appending that. So I'm just appending those events one after another, and we expect it to be saved. So let me also run that one. So EDA. And if you go here, so it executes, it gets those things and created the event. So let's go to Cosmos DB Explorer. Here is our database. So these are our events. So this is our customer created event. Let me scroll. And this is our email updated. But the snapshots, we are saving that in a separate container, because we might have the requirement that the primary key could be different things. Maybe we want to partition them over the email, for example, to make sure, for example, email is unique or something like that. And here is the status at the moment. Okay. So if I'll go, yeah. So to wrap it up, we talked about event-driven architecture. It is useful when we have high volume of events and we have real-time processing requirement. Also, when scalability is a primary concern in our system and we require immediate reactions to things that are happening in our system. We talked about CQRS and event sourcing as some relevant patterns that we could use. They are a good fit into this architecture. They help us to separate the read and write model. The event sourcing brings audit logging and tracking state changes, especially when it's a critical thing like a finance system or something like that. And how Azure Cosmos DB could help us with its features like global distribution, performance and guaranteed performance and SLAs, the change fit mechanism, and automatic indexing. As I mentioned earlier, if we have just point reads, which we had in our scenario, you could disable indexing and create your read model on different containers. And also you could send the data to some other services that are better suited for search capabilities. And it supports a multi-model and multi-API support, graph databases, vector searches, document database, key value database. Yeah, I think that's kind of everything I wanted to go through. So thanks for participating, and I hope you enjoyed this time. And please keep in touch, and if you have any questions.
Cool. All right, let's take a look. Right now, I think we hit all the questions we have. Well, we'll give everybody a minute. If you do have a question, we have our guest for a couple more minutes. And if we don't have any questions, we'll carry on. But you know what? This gives us a good chance for Askia to come in and kind of help us start closing out. You want to give us a little bit of our closing shopkeeping that you got to do?
Yeah, of course. We've got a survey slide, which is here. So we definitely would appreciate any feedback that you have about the session or future sessions or sessions in general. We'd love to get feedback. So if you could take some time to just do that, the event ID code for this particular session is going to be 22816. And we definitely take it all into consideration. So appreciate your time and your input.
Got it. Thank you very much. Sorry about that. Wrong button. Okay, cool. So thanks. We do have one more question. I think I know the answer, but I'll let you answer it. So Thomas wants to know, is Cosmos DB a hierarchical database? From what I know, the way that data is organized, into database containers and items, yes, it is. If there's another representation of hierarchical, like regarding like partition keys, that could be a different answer, but for the most part, yes. Do you have any other comments to add?
No, I think one of the things that also maybe to consider when you're dealing with like very big enterprises is like this hierarchical partition key that you could also use like to achieve this amount of data that you want to manage for each tenant or each kind of part of your system. So
got it. Cool. All right. Well, we've got one more question here. Is it necessary to store events in a different database for scalability?
you mean like a different database than the Cosmos DB?
Yeah, I'm not really sure. Rocky, if you want to update your question, feel free. We're not really sure about your answer, or you can follow up with us via LinkedIn or anything like that. That being said, we're just about out of time, and so I think it's time to start closing out, giving everybody what they need to check out next. So Shahab, what's the best way for someone to get in touch with you?
I'm active on LinkedIn and GitHub and also Twitter or X platform. My handle is at Shahab Ganji, and yeah, that's I think
Great.
the best way.
Sounds good to me. Askia, thank you as always. Appreciate your assistance in getting this done. And then Shahab, thank you so much for being part of it. It was really great. You gave us so much information. So I thank you so much for your time. Everybody, we'll be back again next month. We've got another one of these. We've got more AI, more design, more all the things that go into building applications with Azure Cosmos DB. And that being said, let's give you everybody the big wave goodbye. Thanks for joining us. We will see you next month. Thank you, Shahab. Thank you, Askia. We will see you next time. Take care, everybody.
All right. See ya.
Bye. See ya.